Today we're going to start by solving this equation, which is very easy, and then we're going to use it as sort of a template to talk about other equations that some students tend to have trouble with. And my intention will be to show that it's actually all the same thing if you're focusing on the important aspects of what you're doing in order to solve this equation. So for this one, the first thing that I'm going to do is to multiply both sides of the equation by 5x plus 6 in order to get rid of this denominator. Then we want to subtract 3x and also to subtract 42, because then we got all of the x's on the same side of the equation. So finally, I'm going to divide both sides of the equation by 32, which is multiplying the x. I've also switched the left and the right side of the equation now, just so that my sentences are starting with x is equal to. And in this case, I can simplify a little bit this fraction, and there you go, problem solved. So the first modification that I would like to do in order to make the equation look slightly more complicated is to just change this number on the right instead of 7. I want to change the 7 for a more complicated number, but before I do that, I would like to keep track of where the 7 is going as I solve the equation like this. And immediately I realized that I can't see the 7 anymore. The 7 is both in the 35 and in the 42. So I would like to keep it there instead of actually doing the multiplication 5 times 7 and 6 times 7, so that I can see where the 7 went, because that's what the new number that is going to replace it is going to have to do the same thing. So this 42 is going to be a 6 times 7. The 35 is 5 times 7 as well. And now the 32, I'm not going to be able to write down 32 anymore. That 32 was 35 minus 3, which is actually 5 times 7 minus 3, because what happened from this line to this line was just factoring out an x. And when the numbers are simple, such as 35x minus 3x, a lot of people don't tend to think that that's what they're doing when they say that 35x minus 3x is equal to 32x. People can think of it in terms of collecting like terms, or in terms of just, this is a simple subtraction. But a lot of people don't think of that as factoring out an x. I'm trying to point your attention to the fact that it is, and the minus 38 on the left side is also not going to be written in that way. It's just going to stay as 4 minus 6 times 7, because the 7 is now going to become something else. The simplification in the end is not going to happen because the numbers are going to change, and the 38 and the 32 are going to be rewritten in this new way. Actually, it's not a new way, right? It's the old way. Is what they were before I actually did the calculation. So this is the 32, and that's the negative 38. Actually, I could have included another line here way in the beginning, which is after I multiply both sides by the denominator of the fraction, but before I did the distributive. And then I want to point out that from here to here was the distributive operation that was happening. Distributive is the opposite of factoring something out, which is the thing that I'm doing later. Of course, I'm not just doing one operation to undo the same exact thing later. I am distributing the 7, and then later on I factor out an x, which is something else. And that is the whole point of how this kind of solution works. First you distribute something, and then you rearrange the terms, and then you factor out something else. The rearranging is what happened in this line here, when you've moved both x's to the same side of the equation with the intention of factoring it out. Okay, so now let's see what would happen if instead of 3x plus 4 over 5x plus 6 equals 7, then it was that same fraction equals to the square root of 7. How would you solve that equation from the beginning? Just I give you this problem if I hadn't showed you this before. Well, hopefully what you would do is that you would multiply both sides of the equation by this denominator, and then you would distribute the square root of 7, rearrange the terms, leaving both terms that contain an x on the right-hand side. Then you would factor out that x, leaving everything else on the left side. And then finally, you divide both sides of the equation by the number that is multiplying the x, which happens to be 5 root 7 minus 3. So there you go. It was the exact same equation with the exact same solution, only with a slightly different number. Uglier numbers tend to make people more nervous because there's no immediate cancellations that you can do with them, so the expression just becomes bigger and bigger. But that's okay. That's what I mean when I say that you have to focus on what's relevant about the situation. And whether the numbers are canceling out, whether the expression that you're writing is becoming big or small, if it's ugly or pretty, none of that is relevant. What is relevant is that you get rid of a denominator, then you rearrange your terms, and then you factor out an x and divide by whatever's multiplying it. The same thing can be done if instead of a number there, I have a variable. And this kind of thing is going to happen when you're trying to find the inverse function of rational functions, because right now this looks just like a rational function, right? And when you want to find the inverse of the rational function, the first thing that you do is you switch the letters. You're going to switch the variables x with y. And then you're going to keep track of everything that that x needs to do. Is the same thing as the square root of 7 was doing before. First, you take the denominator 5y plus 6 and multiply it. Now you're going to distribute the x. You're going to rearrange the terms, making sure that both y's are on the same side, because that's the variable that you're trying to isolate now. It's y, it's no longer x. X is now just playing a role like the 7 was in the first equation. So now you're factoring out this y, and you are dividing both sides of this equation by 5x minus 3. There you go. That's your inverse to your rational function. Now we can try to do something that looks completely different. This is an exponential equation in which the both bases don't have anything to do with each other. Of course, if instead of a 5 we had a 4 here, that would make it into a completely different problem, because 4 is equal to 2 squared. And then you can use a power of a power, and then you get the same bases on both sides, and everything just becomes a simple linear equation that we like to solve. But with 5 is not going to be so simple, because 5 is not 2 to the power of something in a straightforward way like that. So instead, what we think of to do here is to use logs. I'm taking the log of both sides of this equation. And after I've done that, I have exponents inside of the log on both sides of the equation, actually. And then I'm going to use the rule of log that tells me how to get rid of that exponent inside. And now the thing that I would like you to notice is that this is just a linear equation. There is a little bit more to do here, like we do need to do a distributive with this log 5 on the left and with the log 2 on the right as well. But either way, what we're going to get is on the left side, we're going to get a term with x and a term without x. And on the right side, a term with x and a term without x. That's exactly what a linear equation is. So it is the same thing. Although we get a little bit of a choice here, right? Because this blue log that I'm using, it could be any base. You can use base 10, like I've written here in a way that suggests that the base should be 10. But if you use base 5 instead, then this part is going to be 1, because log base 5 of 5 is 1. And if you choose base 2 instead, it is the one on the right-hand side that is going to disappear. You can do any of those things. I think that for today, I'm going to stick to base 10. I'm struggling to decide in what order to write these things here in this term, because it's 3 things being multiplied together. It's 3 times log of 2 times x. And usually when I multiply 3 things and just one of them is not a number, like x, I tend to put it on the right side, which is what I did here. But on top of that, I have chosen to not put the parentheses in the numbers of any of my other logs. So it's looking like this might be log of 2x, which it is not, and I really don't want it to look like that. I could fix it by just putting parentheses in this one, but then it looks a little bit strange. Why does this one have a parentheses and the other ones don't? Another option that I have is just to change the order. 3 times x times log of 2. I'm going to stick with this one for now, but please don't forget that these are 3 things being multiplied together. And I want my x's to be red. I want them to stick out in a different color. Because you remember what the next step is, right? We want both of the x's on the same side of this equation, and everything else in this equation is a number. Some of them are pretty numbers, like 2 and 3, and some of them are ugly looking numbers, like log of 5 and log of 2, but we don't care. That's not relevant. That's not what we're focusing on. Nothing is going to cancel out if we add a 5 to a log of 3, for example. But we don't care. That's not important. The important thing, the relevant steps that make all of these equations that I'm solving today be the exact same equation, is that we want all of the x's on the same side, all of the other stuff on the different side, and then we want to factor out the x. So let's do that. Now everything is where it should be. I'm just going to factor out the x. Notice how the problem that I was having with the three terms multiplied, that's not happening anymore because now it's just two terms and both are numbers. So 3 log 2 is the natural order in which to write those things. And then I've divided by the number that was multiplying the x. The x is isolated. X is equal to a bunch of stuff that is just numbers. So this is the solution to the equation and we're finished. Some people like to try simplifications now. For example, 3 times log of 2, isn't that just log of 8? Well, yeah, it is. So you could do that, but you don't have to. And then you notice that the numerator and denominator, both of them have subtractions of logs now as well, right? And that is something that we know how to simplify with a rule. And again, I'm doing these things now because I know that some people like doing them, but I'm not sure that I would do them if I was just solving this question on my own. I want to stress that this is not necessary. More importantly than telling you what's not necessary is telling you what's not allowed, right? Because the rule of subtracting logs turns into a division, which makes a lot of people confused that a division of a log by another log should turn into a subtraction somehow, but it doesn't, okay? Don't make up rules. If you're confused as to which rules exist and which don't, just look at the formula booklet. Don't make stuff up. The only thing that you would find there that has a log over another log is the change of base formula. So again, this is pushing it a little bit or a lot. But if you want to simplify this, the only way would be this, because now I've used the change of base formula and it turned into the log base 5/8 of 2 over 25. Now, I've never actually seen this happen, but if they wanted you to do this specifically, then they would say something like this sentence that I wrote here now. Give your answer in the form log base p of q, where p and q are rational numbers. And if they don't do that, if they just say solve the equation, please stop here. Although after finding the correct answer, which is this one in the orange box, if you keep doing further work after that and your further work happens to be wrong, they shouldn't take away marks for further working after the correct answer. But what you're just wasting time, so I don't recommend doing it anyway.